Now let's talk about the last kind of state element that we'll talk about in this chapter. This is the D flip-flop. And you'll understand its name once we talk about it. It's the internal circuit. So the D flip-flop, D again stands for data, has two inputs, just like the D latch, clock and D. And here are the symbols, the D flip-flop symbols. It has D input, and then it has this triangle on the top input. And that top input is the clock input. We don't even have to label CLK because that triangle indicates that it's clock and indicates that this circuit is edge triggered. So this triangle indicates that it's edge triggered, and that means that this circuit responds to the edge of a clock. So what is a clock? Well, a clock is really more of kind of a click, right? But don't call it click. But it goes high, low, clock goes 1, 0, 1, 0, 1, 0, 1, 0. And everything in a synchronous sequential circuit is synchronized to the clock. And so when we get an edge, this is called the edge when it goes from 0 to 1. This is the rising edge. The circuit is synchronized with that rising edge. And so the D flip-flop responds to the edge of the clock. So here's a bigger view of the flip-flop, and we can also even write a smaller version of the flip-flop where we don't even label D and Q and don't show Q bar for conciseness. But this is still D, this is Q, and here's our clock. And we'll most often use this one symbol for our D flip-flop just for conciseness, right, and less clutter in our circuit. So the function is that this D flip-flop samples D, the input, on the rising edge of the clock. So our D latch was level sensitive in that whenever clock, this input was high, for our D latch, just D passed through to Q. But now, so this is for our D latch, that's how that worked. It was level sensitive. Whenever clock was high, D passed through to Q. When clock was low, Q equals Q previous. But now, for our D flip-flop, D passes through to Q only at the rising edge of the clock. So it samples D, so D flows through to Q only at the rising edge of the clock. And every other time is memory. Q equals Q previous. So again, when clock rises from 0 to 1, D passes through to Q, otherwise Q holds its previous value, or in other words, it has memory at all other times. Q will only change then on the rising edge of the clock. So we have very tight control over when our output Q of a D flip-flop is going to change. And it's called edge triggered because it's activated on the clock edge. And so here we have our picture of our clock and the edges of that clock, particularly the rising edges. So how do we build a D flip-flop? The internal circuit is two back-to-back D latches. So here we have latch 1, and here we have latch 2. And this is the D latch that we just talked about in the prior state element. And we have clock coming into the rightmost latch and clock bar. So we invert clock and get clock bar going into the leftmost latch, or L1. And this L1 is called the leader latch, and this is the follower. The right L2 is the follower latch because the first latch, the leader latch, is going to feed in D into this internal node N1, and then the follower is just going to follow whatever that latch did. So let's talk about the timing of how D passes through to Q. Okay, so when clock is equal to 0, so here's our clock edge, and we'll look at that. So when clock is equal to 0, there's clock being equal to 0. Well, let's see which one is allowing, which one is transparent. We're allowing its D input through to Q. Well, L2 isn't. L2 is what we call opaque or cut off, right? This internal node N1 cannot pass through to Q. So when clock is 0, L2 is opaque, but L1 is transparent. So when clock is 0, clock bar, remember this is the inverse of clock bar is equal to 1. And so this leftmost latch, L1, allows D through to this internal node, right? You can't see the difference of, this happening on the output, Q, but D is being passed to this internal node, N1. Now, when clock equals 1, so clock transitions from 0 to 1 here, and clock becomes 1, well, what happens? Clock bar becomes 0, and now this L2 becomes transparent and allows N1 through to Q, and because we have a 0 on this L1 D latch, now L1 becomes opaque and does not allow D to its internal node. So right at this edge, right before that edge, D got passed to the internal node N1, and then right after this edge, clock equals 1, N1 gets passed through to Q. And that won't happen again, right? This kind of passing through of D to Q won't happen again until the next rising edge, the 0 to 1 transition. So again, when clock is 0, L1 is transparent, L2 is opaque, and it allows D to pass through to N1. And then when clock equals 1, L1 is now opaque, and N1, this internal value that was just sampled the value of D, gets passed through to Q. So on the edge of the clock rises from 0 to 1, in other words, right? That's what the edge of the clock is. D passes through to Q. D is sampled, right? The value of D passes through, really it's in lockstep, right? Right before the clock edge, when clock is 0, D passes through to the internal node, and then right after the clock rises to 1, it gets passed to Q, that internal node. And so that's why it's called a flip-flop, because only one of these latches is active or transparent at any given time, and they flip-flop their state, right? This one's transparent, this left latch is transparent, and then after the clock rises, now the right latch, L2, is transparent, and keeps going back and forth. Flip, flop. Right. So let's compare how a D latch and a D flip-flop work. So here's our symbol for our D latch. And it looks very similar to the D flip-flop, except we just have a clock input up here. And now our D flip-flop has a triangle here indicating edge triggered for the clock input. So here we have our clock, and let's start with the latch. So we'll start with this leftmost circuit here. We know that the latch is going to be transparent or allow D to pass through to Q only when clock is high. So it's level sensitive. It's sensitive to the level of the clock. And so we can draw, we can even draw kind of lines here. This is where Q could change, is when clock is high. That's the only possible time. All other times between that will be memory. So when clock is low, the latch will retain its state. Okay, So here we go. At time, at the time when clock rises, when clock is high, Q just follows whatever D does. And so D is low and then high. And then clock goes low. And so the D latch just retains whatever state it had right before the clock went low. Now, when clock goes high again, right, here's the clock going high again. Again, it passes D through to Q. Clock goes low again and just retains that state that it had right before the clock went low. And then finally, the last time clock goes high, well, D is still high, so it stays high, right? D just follows whatever D does. Okay, now for our D flip-flop. Well, D flip-flop's a little bit simpler because all we have to worry about is this rising edge. So we're going to sample D when clock transitions from 0 to 1. And be careful, some people try to include that. The falling edges, don't do that. It's just for rising edges of the clock. And so we can sample what D is at those rising edges of the clock and put that value down for the output or state being stored in our flip-flop. So we have 0, and then we have 1, and then we have a 1 here. And what happens between those? Memory. So we get 0, it stays there until the next rising edge. Now it goes to 1, samples D, gets a 1, samples D again, happen to be a 1 again. But between those samples, memory, it just retains whatever it had. And so we only have to worry about Q changing at these very discrete points in time. It's only going to change at the rising edge of clock. And so one question is, well, what is the value before we get our first edge or the first time clock goes high? Well, we don't know, right? We turn this thing on, it could be 1, it could be 0, and so we just put that kind of value. Could be 1, could be 0, we don't know. And so we put both to say we're not sure what it is when the circuit just turns on before we get the rising edge of clock.